Okay, we're gonna do some notes for lesson 3.1, first part of chapter 3. Chapter 3 has a lot to do with exponential functions, and then we'll move into logarithms down the road. So we're going to start with exponential functions and logistic functions. First, we need to review evaluating the following expressions, and it says we can do these things without using a calculator. So first thing we want to do is think about what does it mean to be a cube root, and we can think about the fact that it was what is multiplied together 3 times in order to get negative 125. Unlike a square root, you can take a cube root of a negative because it would be negative 5 times negative 5 times negative 5 is negative 125. Much like square roots, you can take the cube root of the top and the cube root of the bottom separately. What do you multiply together 3 times to get 27? 3. What do you multiply together 3 times to get 64? 4. Be 3/4. 27 to the 4/3. We do not need to do, you don't need your calculator because you can rewrite this as the cube root of 27 all to the 4th power. And as we saw right up top there, the cube root. Remember, whatever this denominator is over here is what you're taking the root of. So the cube root of 27 is equal to 3. 3 to the 4th is 81. In terms of those fractional exponents, you got to remember that the square root of, say, 16 is equal to 16 to the 1/2. So that's why the cube root of 27 is equal to 27 to the 1/3, and so on and so forth. Moving things up and down and all around, there's 2 ways to do this next problem. A to the negative 3 all squared. First thing you could do is raising a power to a power, you multiply a to the negative 6th. It says make sure it has a positive exponent. That means the whole thing can shift to the bottom, and we get 1 over a to the 6th. Second way to do it would be to say I'm going to make it 1 over a cubed all to the 2nd power, which means we can square the top and square the bottom, and you get the same answer. If you use your calculator to do this, there's a spot to do the 5th root. You can find that under Math, and then go to it's Math, and then over to, or it's down to the 5th one where it says x root, and you can put in a 5, so you can do the 5th root. 5th root of this guy here, I think it's 1.5, isn't it? 3.71293. It's 1.3. So we put a 5 in for the x, 3.71293, and we get 1.3. That means 1.3 multiplied together 5 times gives you this thing. The other thing you can do is you can do what we did up here. It's probably even easier. You take your 3.71293, raise it to the power of 1/5, or raise it to the power of 0.2, and you get 1.3. So some calculator reminders there, and how to work with fractional exponents. They're just roots. Okay, we got them right. Next, we're going to do exponential functions. We're going to be in the form of y, or f of x equals a times b to the x. So f of x equals, or y equals a times b to the x. So if we think about y equals a times b to the x. The first thing we have to do is we need to understand order of operations. It says a is non-zero because if a was 0, we would have y equals 0, and this would be nothing. When x is equal to 0, right here, x is equal to 0, anything to the power of 0 is the number 1, and therefore you get the initial value. So our a here will always be the starting point. So when x is 0, if you're talking about an ordered pair, you'll always have a. And that's a really good thing to think about when you're talking about population. Starting population will always go there. So we're going to do a bunch of things with like so far we've done, y equals mx plus b, and we've given 2 points. Can you find the equation? And then we did y equals a times x minus h squared plus k. And given the vertex and the x and y, can you solve for a? And then we did it with polynomials where we solved for a as well. And this is just going to be right along those same lines. Can you find the exponential equation given this different stuff? Determine the formulas for each exponential function g and h. These are 2 separate problems. X values on the left, g of x values over here. When x is 0, we just said, this will be our initial value. So we're going to use that initial value to determine the fact that what a is. And you could plug that in and say, well, y, or g of x, is equal to a times b to the 0. And that means b to the 0 is 1, so a is 4. So there you can see it algebraically that a is 4. So if you understand that when x is 0, that's going to give you your initial value every time, things will go a little bit easier for you. The next thing I'll do is if I'm looking for the other stuff, I can use this 112. So when y is 12, a is 4, and I get times b to the 1. So I divide by 4 and divide by 4, and lo and behold, b is 3. Well, that means b is 3, so my equation is g of x equals a times 3 to the x. And if you remember back to the previous screen, it says the 3 was going to be the base. And what does it mean to raise a base to an exponent? It means that the base is repeatedly multiplied. And this was our initial value. So what are we repeatedly multiplying by here? 3. Where are we starting? 4. 4 times 3 is 12. 4 times 3 squared is 4 times 9 is 36. If I wanted to know 9, 4 times 3 to the 9th, probably need my calculator for that one. One on the right, h of x, clear this out. H of x, again, I've got 0 and 8. My repeated multiplication is 1/4. It's just going to be h of x equals initial value times, what are we continually multiplying by? 1/4 to the x. Check your work. Put in 1. 8 times 1/4 to the 1 is 2. Absolutely. Put in a few more. So you can get them from a table if you know the initial value. Very helpful. If you know the repeated multiplication, you're basically done. Okay, we got them right. Exponential growth and exponential decay is something that you've been working with in the past. So when we're talking about when we're talking about y equals a times b to the x, if b is going to be greater than 1, a number bigger than 1, then we are going to be a growth function. Growth. This is for positive a's now. So if we think about y equals 2 to the x, y equals, well, 3 times 2 to the x. Exponential growth, it's going to be getting bigger. B is less than 1, but if it's going to be a fraction, we're gonna have a decay value. Should also say that less than 1, greater than 0, I guess. We're going to be a decay function. Transformations, if you remember back to our transformations for parabolas, quadratics, when we add or subtract to just an x value, we move things left and right, and it's an opposite idea. And when we add or subtract to just the to the entire function, it's going to be an up and down. So if I said this minus 2 is just the x value, it's going to be very similar to when we did y equals a times x minus h squared plus k. Went up or down, or left or right, h units, went up and down k units. Going to be the same idea here. You're going to have, this is going to be to the right 2 units. Okay, if I wanted to go up 2 units, it would be f of x equals 2x, and then the whole thing plus 2. So if you added the whole function, it's up and down. If you add or subtract just to the x value, it'll be left or right. So all the same transformations hold true. Here's our y equals, we go 2 to the right, and we end up with the 2 to the x graph. 2 units right. So back to, we probably should make note of what does y equals 2 to the x look like. If you think about 0, 2 to the 0 is 1. We'll cross right here. 2 to the 1 is 2. We'd cross right here. 2 to the 2 is 4. Now we start picking up steam. 2 cubed is 8. Must be about up here. 3, 4, 5, 6, 7. Yeah, we're going to be here. And now, why do we have an asymptote at y equals 0? Because 2 to the 1 half, that's the square root of 2. Square root of 2 is 1.414. Be right about here. And then 2 to the negative 1 is going to be 1 over 2. And 2 to the negative 2 is 1 over 4. And 2 to the negative 3 is 1 over 8, and so on and so forth. Oh, I guess 2 to the half. Yeah, that's going to be right here. Sorry. I meant negative 1. Whoops, I can't draw a very straight line. And we go up. There we go. So there it is, moved 2 units to the right. If I took all of these points and went 2 units down, I would just find this important point here. And I would find my asymptote here. And I would mimic this going up like that. If we negate the x values, if you remember, if you negate the entire function, you're going to be reflected over the x-axis. That would be negative 2 to the x. That's the entire function. That's going to be reflected, instead of going up like this, it's going to go down like this. This guy, negating just the x value, remember that reflects it over the y-axis. So it's going to go up like that. There's the graph of it. If you negate just the x value, you go over the y-axis. E, we'll talk about E as the chapter continues. E is just a number. It's on your calculator. You can find it in 2 different spots. Second and the division sign will find you the number E. Don't forget, it's a number like pi. It's an irrational number. Never terminates, never repeats. It's approximately It's approximately 2.71828. you get it if you put this into your y equals and then look at the table as the table grows. What's happening here as we approach infinity, you will approach this number. So if you did an xy table, if you think about this for a second, if I put a 1 in here, 1 plus 1 over 1, that's 2. 2 to the 1 is 2. And then I put a 2 in there. 1 plus 1/2 is 1 1/2, but I'm squaring it. So 1 1/2 squared is 2 1/4. And then the next would be put in a 3. 1 plus 1/3 is 4/3, and you're gonna cube it, and you're gonna get 2.37. This will continue, and you could see it on a table if you wanted to. As you climb up, this is the number that you will approach. This is going to be used when we talk more about some continuous growth or some continuous, a lot of financial implications in E. You can also use an E. Notice the difference in the similarities between these two functions. If you're talking about this is exponential growth, this is exponential growth. The difference here is in this guy, we've got B is greater than 1 for growth. And in this guy, E is a number, it's 2.718, so the K is positive. So if you have a positive exponent, you get growth. And if you have K is negative, less than 0, you get decay. So we'll work with that as we continue in the chapter as well. Growth function goes up, decay function goes down. Last one here, we've got a little example problem. So we're going to have San Jose exponential growth. What is the growth factor? What's the population in 2010? And when will the population reach 1 million? So what we can do is first we can write an equation where we've got initial value. So this will be A. And we've got 10 years after 10 years. So that's kind of an ordered pair. So at time 0, at 0 years, we're at 782,248. And at time 10, we're at 895,193. So you can put this into y equals a times b to the x, where we have my ending value is going to be 895,193 is equal to my beginning value, 782,248, times my growth factor, which is the base, which is b, raised to the power of 10. So the first thing you're going to do is get that b to the 10th by itself. So I can take my 895,193 divided by 782,248, and I get this 1.144 is equal to b to the 10th. Now, how do you undo something to the 10th? You can take the 10th root, but also remember we could raise both sides to the power of 1/10. So I'm going to take my answer that's in my calculator and raise it to the 1/10, and I get 1.01358. That's enough. So what's the growth factor? This is the growth factor, but if you remember back to what does it mean to be exponential growth, we are growing by 1.358% per year. That's what you get in this little guy there. What's the population in 2010? Well, take your y equals 782,248 times my value of b raised to the 10th. Just type that thing into your calculator, and you could actually use you could have a more exact value. Oh, now I need 20. Excuse me. This should be a 20. Almost made my first mistake of the year. I got 1,024,445. 1,024,445. 45. That was for 2010. When does it reach? When does it reach 1 million? There's a few different ways you can do this. You can do it on your calculator. We haven't done logs yet, so we're pretending we haven't done logs yet. You can put this y equals the 782,248 times the 1.01358 to the x. Put this into your calculator. Take a look at the table, and you can see when it crosses over into 1 million. I think it's sometime in year 18, if I remember correctly, 18 or 19. You can also put this in there, and then put y equals 1 million in there, and calculate the intersection. You just got to worry about, can you see the window? I think you got to go 0 to 20 on the x's, and you got to go 0 to a million on the y's, and calculate the intersection, and that'll tell you the exact date where it reaches a million. I think that's it. Last thing. There's a problem like this in your homework. This is called a logistic function. If you remember back to when we did our 12 basic functions, talked a little bit about this back in chapter 1. And they graph like this. So they look like they are exponential, and then they level off. And this comes up in population because you get a population, there's an asymptote there, this is supposed to go up here, where you can't get any bigger. So New York is near reaching its maximum sustainable population based on the fact that every square inch has been developed. The limit to growth, there's a question in your homework. This is going to be the limit to growth. So whatever that value is there is the limit to growth. And then you can solve this guy. Or this is useful in figuring out where you are on the step here. Both of these things are the same. But the number that's on top is what your maximum sustainable population is. Okay, that's it for 3.1, and hope you enjoyed it because it was a good time.